Last time we talked about market-based policy instruments, assuming tacitly that the market we were trying to regulate, the market that generates environmental externalities, is a perfect market. Today I'm going to relax that assumption in three ways. I'm going to talk about market power and what that does to taxation. I'm going to talk about asymmetric information and the resulting adverse selection and how to combat that. And I'm going to talk about imperfect enforcement. Just a reminder where we are. This is the last of 3 lectures on policy instruments for environmental regulation. Let's start with market power, or actually let's start with a situation without market power. So there is a demand for a good Q and a price P. So what you're looking at here is a demand function as well as the inverse demand function. And what you can see is that it's linear. And in these functions, P is price, Q is quantity, and then this parameter pi is the choke price, the price at which demand goes to zero. So that's the consumer side of things. On the producer side of things, there is a profit function, which is total revenue, P times Q, minus the cost of production, here assumed to be half Q squared. And then there is a tax on production at tau Q. If there's no market power, then essentially the producer assumes that his actions do not affect the price. The first order condition for optimality is that profits are maximized, so the first partial derivative of profits pi to the choice that we make, that is the amount to put on the market Q, must be equal to 0. The pi dq is P minus Q minus tau, should be equal to 0, or the amount supplied is the price minus the tax. Now let's put this market in a Coulomb equilibrium, that is we equate the amount demanded to the amount supplied. So we have pi minus P is P minus tau, or the equilibrium price is pi plus tau over 2, or the equilibrium amount supplied is pi minus tau over 2. Now let's instead look at a monopolist. The demand function and the inverse demand function are the same, profit after tax is also the same, but the key difference is that a monopolist takes into account that the amount supplied has an effect on the price. So the first partial derivative of minus 1/2 times Q star Q squared minus tau Q stays the same, that is minus Q minus T. But the first partial derivative of P times Q is now different. The P remains, but the new element you see here is Q times the first partial derivative of the P of P to Q dP dQ, which in this case is minus 1. And as a result, the supply function of the monopolist is P minus tau over 2. And that is exactly half of what a price taker would supply. As you can see here, it was pi minus tau previously, it's pi minus tau over 2. Coulomb equilibrium, Q equals Q. What we have is pi minus P is now pi minus tau times 1/2, and as a result the equilibrium amount supplied is pi minus tau over 3, which is different from what you would see in a perfect market. And we compare the two on this slide. So the difference is that previously you divided by 2 and now you divide by 3. Let's introduce a social planner. And a social planner wants to maximize the sum total of all the players in the economy. And what we're interested in on the consumer side is the consumer surplus. The consumer surplus consists of 2 components. One is the amount you pay for the goods that you bought, that's negative, and that's minus P times Q. And then we have to integrate under the inverse demand function, and that is the element that you see here. Now, integration is usually hard, not in this case because we have a linear demand function, so we introduce a squared. So the integral is a squared function evaluated from 0 to q. 0 is the point of no demand, q is the actual amount demanded, and we end up with this particular expression here. The social welfare is the consumer surplus. That's the consumer side of things, the total profit pie, the tax revenue that the government gets, and then we need to subtract the environmental damage that is done, which we assume is proportional to the production of Q. We stick in all the elements. Here we have the consumer surplus. Here we have the profit function. You immediately see that the amount that consumers pay for their goods is received by the companies that are in the market, so that cancels, that is just transfer of money. And similarly, the amount of tax that is paid by the companies cancels against the tax that is received by the government, which is again just the transfer of money in a social sense. So the welfare function really is pi minus delta times q minus q squared. The choice that the government needs to make is the tax that is set on production. So the first order condition for optimality there is the first partial derivative of the welfare function to the choice that we make, that is tau, and that should be equal to 0. Now, let's go back to the situation where we have a price taker, social welfare function. We've seen before the optimal response function, the response of the price taker to the tax is displayed here. So we plug that into the social welfare function, take the first partial derivative to tau, and set that equal to 0. So the first partial derivative to tau of this thing, p minus delta, just pops up here. The first partial derivative of q to tau is minus 1/2. So the minus is here, the half is here. We need to use the chain rule, so we have 2q, 2 times q we have here, and then again first partial derivative of q to tau is minus 1/2, so we have 2 minus signs here, and 2 over 2, which nicely cancels. That should be equal to 0. Multiply both sides of the equation by 2, and what we have is that minus pi plus delta plus pi minus tau is equal to 0, which implies that tau should be equal to delta. In other words, the optimal tax is the marginal environmental damage. The tau that we're looking at here is your standard PGU tax. Now, let's redo this for the monopolist. Social welfare function stays the same, but the response function is different. Instead of pi minus tau over 2, we have pi minus tau over 3. The optimum follows from setting the first partial derivative of the welfare to the tax tau equal to 0. So dq d tau now is minus 1/3 rather than minus 1/2. So p minus delta times minus 1/3. 2 times p minus tau over 3 times minus 1/3. And what we have is, multiply both sides of the equation by 3. What we have is minus pi plus delta plus 2/3 of pi minus 2/3 of tau should equal 0. So this these two together become minus 1/3 of pi. Delta stays the same, then we bring tau to the other side of the equation and multiply both sides of the equation by 3 over 2, and what we have is that the optimal tax is the marginal damage times 1.5 minus half the choke price. Let's put everything back together. What we're looking at is that in the perfect market, what we want to do is set the tax equal to the marginal damage done to the environment. But in case of monopolistic market, we don't want to do that. There is an optimal tax, but it's a different tax. So why is this, and what's the intuition here? The first 2 points I have made already. So what you have in a monopoly is that the output is suppressed. A monopolist suppresses demand to increase the price. So if you were to apply the Bigot tax and demand is already too low, supply is already too low, and therefore environmental pollution is lower than it would have been in the case of the perfect market, you don't need to work so hard to reduce it further. So that is one thing. But then a monopolist also responds differently to a price change than a supplier in a perfect market would. So what happens here is a different market response, and therefore you would your initial condition is different, your initial situation is different because environmental pollution is less, but also you have a different response of your polluters to your tax signal. That implies that the tax that you impose is different. Now this is the simplest case, and the analytics are very, very straightforward. If we assume linear demand, if we assume quadratic costs, then the first order conditions are nice and linear, we can solve it. We could of course make this far more complicated. Another thing that you may want to consider is that pure monopolies are actually very rare, but other forms of market power are much more common. The same principles hold, it's just that the mathematics become much more complicated and involved, but the fundamental insight remains the same, that optimal environmental regulation is different in perfect and imperfect markets. There are many academic papers on this particular subject. This is something that economists like to do, and they like to impress their colleagues with their mathematical prowess, that they can solve these complicated models. From my perspective, that does not necessarily lead to additional insight. Unfortunately, I've not been able to find much, or any for that matter, real-world applications where regulators respond to the market structure. Essentially, the point that I'm trying to make here is that the regulation that you want to impose depends on market power and those sort of things. But I've not been able to find any regulator who actually has taken this into account in any sort of demonstrable way. So let's move on to the second chapter, where the regulator does not know the costs of abatement. The situation that we're in is that we have decidedly local pollution. That is, externalities are not shared between towns and really, or between facilities. So you can think of groundwater contamination or things like that, things that are very, very local to the offending plant. For simplicity, I'm going to assume that there's two types of polluters, and one type has high costs of emission reduction, and the other type has low costs of emission reduction. But the regulator doesn't, the polluters obviously know this, but the regulator does not know whether a particular facility has high or low costs of emission reductions. So what you would want to do, ideally, because it's a local pollution, is come up with a pollution-specific tax or standard. That would be the optimal solution. So there's no spillovers, so you would want to differentiate taxation. And the high-cost ones you would want to regulate differently than low-cost ones. But the problem is that the regulator does not know who is whom. Another problem may be that the regulator cannot do this for legal or political reasons. It is not allowed to make a distinction between polluters. So this is the situation we're looking at. We have differentiated costs, marginal costs of emission reduction, MCH and MCL. We have a marginal damage function, and really what you would want to do is for the low one, you would want to send your regulation here. This is the amount you would allow or the price you would apply. For the high regulator, for the high cost polluter, this is the amount you would set, or the subsidy or the tax you would apply, but you cannot. So instead you're going to go for, and let's assume that that is what we do, going to go for a price signal that is in between the two, and then you would misregulate both, and you would suffer a welfare loss for both polluters. So what you can do, because essentially you need to do two things here. So you need two instruments, and the two things you want to do is regulate the environment, but also you want, as a regulator, you want the polluters to reveal what they are. And as Tim Bergen showed, if there's two things you want to do, you need two instruments to get it done. So we're going to do two things. We're going to impose an emission standard, that's to regulate the environment, and then we're going to give a subsidy R that is ostensibly to meet the standard, and we're going to structure that subsidy so that companies reveal what type they are. So let's assume that a regulator gives a subsidy R-H to companies that declare to be high cost, and a subsidy RL for companies that declare to be low cost. Let's also assume that the emission standard E varies between high and low cost polluters. Now, it makes sense to, if the aim is to minimize cost, it makes sense to give the high cost companies a less stringent standard. So we actually don't need to give them any subsidy or any other reward to them for declaring that, and therefore R sub H is equal to 0. These companies, however, may declare to be a low-cost company, and to prevent that, what we need to have is that the costs of emission reduction, if you get a high standard, should be smaller than the costs of accepting the low standard, but still the high cost, and the subsidy, right? So this is the target that is imposed on high cost companies, and this is then the cost if you're a high cost company of accepting this target. This is the target that is imposed on low cost companies, but you are high cost, so this is the cost that you impose. The cost that you incur, and this here is the subsidy that you get, right? Now this one is obviously greater than this one, but if you then subtract the subsidy, that is not necessarily the case. For the low cost firm, a similar reasoning holds. They are low cost, but they can declare to be high cost instead. That means that they get a less stringent target. They get a less stringent target, but they forego the subsidy that is given to low cost companies. So the condition for both to tell the truth, you see here displayed at the bottom, where RL has to lie between the cost difference for the low cost company between the low standard and the high standard, and for the high cost company between the low standard and the high standard. Graphically this looks as follows. Here we have the marginal costs again. The low cost companies get a different target, right? So if you are a low cost company, then this is the cost savings that you get from pretending to be high cost if you're low cost, and if you pretend to be low cost if you're high cost, then the loss that you suffer is this amount, which immediately implies that in order for this to work for both companies, your R needs to lie in between those two trapeziums. That is, R needs to be something like this diamond that you see here. Now this may sound terribly involved. It works in theory, but it seems unrealistic. Legally and perhaps politically, there is no problem. Target differentiation, as long as it's based on an objective criterion, is legal, and that also goes for self-declared criteria. And we often see that smaller companies are treated differently than larger companies, for instance in VAT, but also in environmental regulation. If we look at, for instance, nutrients regulation that comes out of livestock, let's say hog farms, then farms with fewer than 500 pigs are treated differently than farms with more than 500 pigs. So that is perfectly legal. Giving government grants conditional on certain conditions is also commonplace. You're not allowed to discriminate, but you are allowed to give subsidies for very specific technologies, and if those technologies are more suited for small companies than for large companies, you essentially, but not legally, differentiate and perhaps discriminate between small and large companies, and the same goes for capital subsidies. So what the regulator needs to do is combine those two, target differentiation and conditional grants, in the right way to induce truth-telling. But yeah, that still sounds like something that may not be, or our dear civil servants may not be quite up to this. You would be mistaken there, and I'm going to show you in a minute. And recall that sort of the theory said that really the subsidy should go to polluters with low cost emission reduction, because that induces truth-telling for both the high cost and the low cost polluters. And the example that we're looking at here is from France, and it's a slightly older paper, as you can see from the graphic quality. On the horizontal axis we're looking at the log of the cost of emission reduction. On the vertical axis we're looking at the subsidy that was given, and then the model predictions are given in the circles that you see here. The theory predicts polluters with low costs of emission reduction should have high subsidies, and that polluters with high costs of emission reduction should have low subsidies. That's the prediction, and then this guy found this data, and those are the crosses that you're looking at, and what you see is that that is indeed what happened. The subsidies went disproportionately to those with low costs of emission reduction. And the example here is the Adour-Garonne Water Agency, where the agency concluded contracts with 185 polluters of the water, obviously, The contract revealed the investment that those polluters would make in abatement technology, but not the costs of abatement. That remain private information. And the contract also specifies what subsidies were given, and those subsidies could either be direct subsidies for buying particular equipment, or concessional loans, so loans at a market rate, at an interest rate that is below the market rate. And then this was to reduce biogenic oxygen demand as an indicator for water pollution. And not only how much was generated, but also how much of this stuff is discharged into the surface water. And then in addition, a tax, not a standard as in the theoretical example, the tax was placed on the amount of BOD discharged. And what the graph shows is that the regulator definitely got a sign right, that the subsidies should go disproportionately to those who actually need the subsidies least. That is, those who have actually a small cost of emission reduction. And actually got the magnitude, the size right as well, not only the sign but also the size. So this is actually quite impressive when you think about it, that this agency seems to have employed a fairly smart economist who knew how to design these policy instruments. Third topic, third chapter for today, third and last chapter for today, is enforcement. So far, we have assumed that if there is environmental regulation, if there is a tax, then polluters obey the law. And if the government says you should reduce your emissions, they do so. And if the government says you should pay your taxes, they do so. That is, of course, a tall assumption, so let's relax it a little bit. So we're going to consider a polluting firm with total costs TC of emissions E, and the costs C are the costs of production, and that depends on the emissions that you generate. Just for simplicity, we omit everything else, but then there's also a fine that would be imposed if, and that fine would only be imposed if your emissions E exceeds the standard that is imposed S. And then that fine consists of three parts. One, regardless of how much you violate the standard, there is a fixed part, a fixed fine at D. Then there's also a variable part that is F, and that depends on the amount that your emissions exceed your standard. So this is not a function, but this is just a variable fine. And then, of course, it also depends on the probability pi of being caught. But if you are a good boy, then and your emissions are below the standard, then of course the fine equals 0. Two situations may arise, one interesting, one not. In the top graph, the fine is extremely high. And that means that the company simply has no interest whatsoever in exceeding its standard, because what you see is that if you go above S, then your costs just rise. In the second situation, the fine is not high enough, and what you see is that the company actually would go here, because if you exceed your standard by a little bit, then the marginal costs actually are going down, and the marginal cost and the total costs are minimized. The marginal cost is 0 at this particular point, where it's actually rational, despite the fine, to exceed the standard. And this is, of course, the interesting case. If fines are so high that everybody complies, then everybody complies, and there is nothing to analyze or to talk about. If it is optimal to exceed the standard, then the total cost function, you see displayed here, That's the costs that you incur if you have emissions E, plus the probability of getting a fine times that fine, and the bracket is wrong in the wrong place. So that is your total cost. You want to minimize that cost by choosing your emissions E. So first partial derivative of total costs to emissions is the CDE plus pi times F. D drops out, S drops out. So the first order condition is that the negative of your marginal costs should equal the probability of being fined times the variable fine, pi F. Now that is the response of the companies, and then if you want to sort of like see this in an efficiency context, and you want to impose something like a good tax, but it's not a tax, you impose a standard, but if you exceed the standard you go above the fine, and that is what drives the behavior. So you want to set pi times F equal to the marginal benefits of emissions. What you then find is this expression here, where the fine you want to impose is not quite your good tax, but your marginal damages of pollution divided by the probability of getting caught, pi. So if we are in a situation of imperfect enforcement, you don't really want to impose as your tax the marginal damages, but really the marginal damages divided by the chance of getting caught. And of course, if pi is 1, that is a probability of 1 of getting caught, then you just are back in the situation that you impose a good tax. But if not, you need to correct that for the chance of enforcement. Now, this is actually something where regulators are keen on working on these particular problems, and there is a reasonably large empirical literature that shows the effects of these. And I'm going to give you 3 examples, and the first 2 are for pulp and paper. Why pulp and paper? Because that's actually a dirty industry, not only very heavy on energy use, because essentially you need to take a tree and bash it up until it becomes paper, but also lots of chemicals are involved. So pulp and paper is just a dirty industry. And here we're looking at a study in the late 1980s. They had monthly data for 46 plants, and the question was, do the discharges of these plants respond to the inspection regime? We're interested in 2 particular environmental issues. One is again biogenic oxygen demand, and the other is total suspended something in the water, and we can measure that in absolute terms, or we can measure that relative to the norm. And then there's a whole bunch of control variables that are not particularly interesting, but the thing that we are interested in is the inspections. And what you see is that in the same year that there is an inspection, your discharges fall significantly, so in 3 of the 4 cases. This one is not significant, but that is of course a bit of mismeasurement. It's actually in the month after, because the inspection may come on the 30th of the month, and therefore you have no time to respond. But if we focus on the month after the inspection, we see that indeed discharges fall, and fall significantly so. So companies do respond to the inspection regime, as you would predict they would. Let's move from Quebec to the US. Now we have 175 plants, and we're a little bit earlier in time. And what we're looking at is the duration of spills into the environment. And the 2 variables of interest are LMONP, which is monitoring, and LNF, which is enforcement. And what you see is that there's no response to companies being monitored, but if there's enforcement regime, if there's enforcement following observed violations of the norms, then you indeed see that spills of chemicals into the surrounding waters falls significantly so. So companies do respond to this. The third example is much more recent, comes out of the Bakken. This is one of the main sources of shale oil in the United States. The issue with producing shale oil, or any oil for that matter, is that typically you also produce gas, and shale is no exception there. Now, that gas that is found is often flared, that is, it's just burned. And the reason for that is that it's a bit dangerous to have it just vented into the atmosphere, so it's actually safer to burn it. But you may wonder, why would you burn it sort of like as a flame out in the open when you can actually also burn it in a gas-fired power plant or in a home for that matter, and use for cooking. And the reason for this is simple, that while oil and gas are often found together, they actually need different infrastructure to transport to the market. And if the fixed cost of the gas transport are too high, then it's simply cheaper to flare it rather than to sell it. Frackers have to report the volume of gas that is flared, but that is self-reporting. There's no independent monitoring of this. The sales that they make of oil and gas are independently monitored, only by the buyers, right? But also there's taxes involved, and that means that the government also monitors this. Now, North Dakota, which is one of the states in the Bakken, decided to regulate the fraction of gas that can be flared. But the other states in the Bakken did not do this. Now, initially people thought this was a bit of a paper tiger, because regulators don't observe the amount of gas flared. They only know the ratio of gas to oil that is common in this particular reservoir, but that mean observation, or that median, actually hides a wide variety. So they know the ratio of gas to oil on average, they know the amount of oil sold and the amount of gas sold. They can sort of take a stab at how much gas was therefore fracked, but not in a way that would ever stand up in court, because of course this particular well is different from any other well, and you can't find somebody for being unusual. You can only find somebody for doing things illegally. So it seemed initially to be a bit of a paper tiger, but people, the frackers, did respond to this. And we know that because of the work of this clever PhD student, Yuan Li, who figured out that you can actually see flares from space nowadays with satellites, because they generate heat, and with an infrared camera you can see that from space. And what she showed was that this regulation was actually not a paper tiger, and companies do respond to the regulation, and that is displayed in this particular graph, where what we're looking at is the amount of gas flaring that is misreported. And what you see is that before the regulation was in place, so this is a diff in diff, right? So we compare before and after the regulation, and we compare North Dakota to the surrounding states. And what you're looking at is that companies responded to this particular regulation started immediately after the adoption, but as soon as it hit it in place, they actually started dishonestly reporting the amount of gas flared, and significantly so in a number of months. So there are models that deal with imperfect market, with imperfect enforcement, with asymmetric information. Some of these things are hard to see in the data, and particularly environmental regulation on the different market structures. That is not something that we know a lot about empirically. There are regulators clever enough to come up with a sort of a composite regulation that makes companies reveal their true cost of emission reduction, which is intriguing. And we also see that companies respond to fines, respond to inspections, and in the final case that we're looking at, actually respond in a perverse way. That's all for this time. Thank you.